Right, in this video, I'm going to go through the AQA A-level Chemistry paper from June 2020. This is the paper. This is paper one, and it's the second half of paper one. I covered the first half in an earlier video. Okay, right. The first question is to do with the reactions of aluminium ions in aqueous solution. Right, this is the topic 5.6, reaction of ions in aqueous solution. Right. Give the formula of the white precipitate B. Okay, right. So what happens here? We form that when we add sodium carbonate to the hydrated aluminium ions, and the reason why that works, of course, is because aluminium ions are acidic, and carbonate ions are basic. So the reaction is going to be, right, you get aluminium H2O 6. Now they act as acids, and they're going to give away protons to form this, which is uncharged, and because it's uncharged, that is the white precipitate. Right, so it's good to bear in mind there that this has lost 3 protons when we're balancing the equation. Now that reacts with carbonate, and what happens is, so you've got carbonate ions. Now, if you give 2 protons to a carbonate ion, you end up forming carbon dioxide and water. And each carbonate is going to require 2 protons, as I said. So this is gaining 2. So we can see that to balance this, the aluminium is losing 3, the carbonate is gaining 2. That means we're going to have 2 aluminiums for every 3 carbonates. So we balance that. The 2 aluminiums, that's going to give us 2 of those, obviously, and that's going to give us 3 carbon dioxides and 3 waters. Okay, so if you check all of that up, you'll see that it is actually balanced. Okay. Right, give the formula of complex ion C. Okay, well, let's have a look at C. What happens with C? It is a white precipitate, but that redissolves. So that's when you add excess of sodium hydroxide. So the condition we need is we need an excess of NaOH. And what's going to happen there is we're going to get, right, we start off with the 6 waters around the aluminium. First of all, we'll replace just 3 of them to form the precipitate, and then replace a 4th one. So you're going to end up getting 4 OH ligands, OH minus ligands there, which means the charge on this is -1. Right, what do we need to balance that? We need 4 OH minuses, and each one of those are going to pull a proton off the aluminium here to form 4 waters. That's the equation for that. Next thing, deduce the formula of the complex ion A. Well, the complex ion A is when you react with EDTA. Okay, now the formula of EDTA is it's got a 4- charge on. You can tell it's got a 4- because of course you need 4 sodiums there. So we're going to react that with an Al3+. Right, it's a hexadentate ligand, so you only need 1 EDTA. So that means that is going to be EDTA 1, Al EDTA 1-. Okay. Explain with the use of an equation why a solution containing hydrated aluminium ions has a pH less than 7. Well, it's because this is acidic. Okay. Why is it acidic? Well, it's because the Al3+ ion withdraws electrons from the water, from the water, the OH bonds in the water, and it weakens them, and it means that they lose protons. Okay, and to show that in equation, then we need Al H2O 6. Each of those is going to lose a proton. H2O5 OH. That will have a 2+ charge, and you're going to release a proton. Maybe give that an equilibrium arrow. It's acting as a weak acid. Okay, that's the end of that question. On to one about equilibrium now. Right, methanol can be manufactured in a reversible reaction, as shown. Figure 3 shows how the partial pressures change with time at constant temperature. Okay, so draw a cross on the axis of figure 3 where the mixture reaches equilibrium. Well, it's about here, isn't it? Yeah. When the lines become horizontal, maybe a little bit further back than that, where the concentrations are no longer changing, it's there. Okay, 6.2, carbon monoxide is mixed with hydrogen in a 1:2 ratio and allowed to reach equilibrium in a flask. Okay, at equilibrium, the mixture contains 0.12 moles of carbon dioxide. We've got to calculate the partial pressure of hydrogen in the equilibrium mixture. Well, what we're going to do there is I'm going to write down the equation. I'll write it a bit bigger so I can write underneath it. So we've got CO and 2H2 going to methanol. And I'm going to write down here start moles, used moles, and equilibrium moles. Right, now it says here we've got 0.23 moles of carbon monoxide at the start. And then in a 1:2 ratio with the hydrogens, that means we must have 0.46 of hydrogen at the start, and we haven't got any methanol. And then it tells us at equilibrium, we've only got 0.12 moles of carbon monoxide left over. So that means we must have used up 0.23 minus 0.12. We must have used up 0.11 moles of carbon monoxide. That means we must have used up double that amount, 0.22 of hydrogen. I haven't used any of that, obviously. So that means how much hydrogen we've got left over at equilibrium. 46 minus 0.22 gives us 0.24. Now, how much methanol have we got equilibrium? Well, for every time we use up 1 mole of carbon monoxide, we get 1 mole of methanol. So that's going to be 0.11 there. Okay. So from that, we can work out the total moles. We need to work out the mole fraction of hydrogen. Okay. So the total moles is that, plus that, which is equal to 0.47. So the mole fraction of hydrogen is going to be the moles of hydrogen, 0.24 over 0.47, which is equal to about 0.511. Okay, and now we know the mole fraction, we can work out the partial pressure of the of that. Okay, so partial pressure, I'll write it over here. Partial pressure of the hydrogen is equal to the mole fraction multiplied by the total pressure. The mole fraction we just worked out is 0.511, and the total pressure is 1.04 times 10 to the 4. So that is going to be 5,310, and the units are kilopascals. Okay, that is our answer. Right, the next question, we've got to state the equilibrium, the expression for the equilibrium constant for Kp. Well, we need to look at the equation over here, products and reactions. So we're going to have Kp, partial pressure of the products of methanol, divided by the partial pressure of carbon monoxide, multiplied by the partial pressure of hydrogen, but we need to square that. State the units. Well, on the top, we've got a partial pressure, so we're going to have kilopascals on the top. On the bottom, kilopascals multiplied by kilopascals squared. So they cancel out. So we've got 1 over kilopascals squared. So getting onto the top line, it's kPa to the minus 2. That's the unit. Okay, so just write down the equation again to remind ourselves. CO2, 2H2 goes to methanol. Right. Some more carbon monoxide is added. So carbon monoxide, not dioxide, sorry. Carbon monoxide is added to the mixture. And it's okay, so add more of that. What will it do to the partial pressure of ethanol? Well, Le Chatelier tells us that if we increase carbon monoxide, it's going to try and decrease carbon monoxide pressure, so it's going to push the equilibrium that way. So it's going to give us more methanol, so the partial pressure of methanol is going to increase. An effect on Kp, no effect at all. The only thing that changes the value of Kp is changing the temperature. Anything else may change the position of equilibrium, but it will not change the value of Kp. And they quite often try to catch you out with that. You can see for this, for example, what they say, what would happen if you increase the pressure? Well, if you increase the pressure, the equilibrium would move to the right, which tempts a lot of people to say that Kp gets bigger, but it doesn't get bigger. The equilibrium moves to the right, but Kp would stay the same. Right, what would be the effect of adding the catalyst on the value of Kp? Of course, it would be no effect. Why not? Catalysts don't change the position of equilibrium. All they'll do is increase the rate of the forward and the backward reaction equally. They don't change the position of equilibrium. Okay. Now here's a 6 marker about to do this structure and bonding and stuff. Okay, so you've got xenon tetrafluoride and phosphorus trifluoride. Okay, so we need to, the melting points are different. Okay, and xenon, fluoride's got a higher melting point. You should give the shape of each molecule and explain why the molecule has that shape and now it influences the intermolecular forces. Okay, so let's do the shape thing first. Okay, now you shouldn't write this down, but I write it down. Then if you do write it down, cross it out. So we drop cross diagram. We've got xenon. Right, it's going to form 4 single bonds. Xenon is in group 0. I've only drawn 4, so it's got 8 electrons in its outer shell. I've only drawn 4 dots there, so that means I need to draw the other 4 electrons for xenon. So that means it's got 2 lone pairs. Well, we won't worry about the fluorines, but each fluorine group 7, of course, each one's going to be like that, but we don't care about those. So we're talking about the xenon here. We have got 4 bonding pairs and 2 lone pairs, which makes a total of 6. So, okay, so cross this out now. Don't need that. We do need that. 4 bond pairs and 2 lone pairs, 6. So the basic shape is going to be octahedral arrangement of the electrons. Of course, we've got 2 lone pairs. So what we end up getting is we're going to have the bond pairs are going to be like this. And we're going to have a lone pair on the top and one on the bottom. they're going to distort the shape of the molecule equally, aren't they? Those one's going to push it down, one is going to push it up. So the overall shape is going to be square planar. And the bond angles are all going to be it's going to be 90 degrees. Now, each fluoride will have a partial negative charge on it. It's very electronegative, of course, but there's no dipole because the molecule is symmetrical. So what kind of intermolecular forces are we going to get? There? We're only going to get van der Waals forces, okay? They might be quite strong, though, because xenon is a big atom with a lot of electrons. And also, because it's square planar, they're going to stack up on top of each other, and you're going to get lots of points of contact. So, so they're going to pack together well. So you're going to get lots of points of contact, strong van der Waals, okay? Which is perhaps why this one is got a higher boiling point than the phosphorus trifluoride. Now let's have a look at this phosphorus trifluoride now, which is probably a slightly more familiar example. Okay, so I'll draw a dot cross diagram again. Right, so we've got 3 bonds. Okay, now phosphorus is in group 5. So that means it's got 3 electrons of its own and it's got a lone pair. Okay, 3 electrons in the bond pairs and it's got a lone pair. So what we're talking about here, we've got 3 bond pairs and 1 lone pair. So the basic shape is tetrahedral. You're going to get trigonal planar though. You're going to have the 4 bonds here, and here's the lone pair. And the bond angle is the same as ammonia. It's slightly less than the tetrahedral. It's got 107.5 rather than 109.5 because you get more repulsion from the bond pairs. Right. So what kind of intermolecular force is that going to form? Well, it will have. You will have that molecule is not symmetrical. Fluorine is electronegative, so you will have a permanent dipole. Unlike the other, the xenon fluoride. It's got a permanent dipole, so you will get dipole-dipole interactions. But you'll also get van der Waals forces. But these two, well, the overall boiling point is lower than xenon fluoride. So the combination of those two must be weaker than the van der Waals forces in the xenon fluoride. Well, why is it weaker in this one? Phosphorus, this is a lot. Phosphorus is a lot smaller atom than xenon. It's got a lot less electrons, and it's only got 3 fluorines, not 4. So you've got less electrons. It's got weaker van der Waals forces. Okay, so that is all you need to. I think you check the mark scheme, you'll get 6 marks if you got all of that down. Okay, you might want to cross out that as well. That's just sort of working out of how many bond pairs you've got and how many lone pairs. Right, now here is a big, long, unstructured titration question where they just give you it and you've got to work it out yourself. Okay, so let's see how we're going to do this. Right, so I like to draw little pictures for these. Okay, so what I'm going to do is, right, you've got to find out the mass of sodium chlorate in a sample of bleach. All right, so what we're doing is we've got a bottle of bleach. And we're going to take 10 centimeters cubed of that out. And that is going to be made up to a volume of 100 centimeters cubed. I'll draw a volumetric plus there. All right, and then you're going to take 25 of this solution out. I'm going to put it into a conical flask. And then you're going to acidify, it says. Okay, so you're going to acidify, adding sulfuric acid. The reason why you need that is you need to provide these H+ ions here. And then you're going to add potassium iodide, and you need that there. And that's going to react to give us iodine in the flask. So we're going to add H2SO4 and Ki, an excess of them, and we're going to end up with iodine, so the solution will go brown. Okay, iodine in there, and then we're going to titrate that against thiosulfate solution, and this is the equation here for that. So let's just draw that. So I've got my flask here, the iodine in it. And here we're going to put the burette with our thiosulfate in there. And the concentration of the thiosulfate, it tells us, is 0.1 mole per decimeter cubed. And the volume we're going to need is 33.5 centimeters cubed. Right, now we have got to work out. So what, when these, it's quite hard to work any style. What can we work out? Well, we know the volume and the concentration of the thiosulfate, so we can work out the moles of thiosulfate. Let's do that then. So the moles, S2O32 minus volume, 33.5 over 1,000 multiplied by 0.1. This gives us 3.35 times 10 to the minus 3 moles of thiosulfate. Now we need to look at this equation here. 2 moles of thio react with 1 mole of iodine, so that we can work out the moles of iodine we had in this flask. So let's do that. So the moles of iodine, that's in 25 centimeters cubed, is equal to 3.35 times 10 to the minus 3 divided by 2, 2 to 1 ratio. That gives us 1.675 times 10 to the minus 3 moles. Okay, now this is in 25 centimeters cubed, but look, what did we do here? We scroll up here. We had a total volume of 100. So that means that if we want to find out the moles of iodine here, we're going to times that number by 4. 4 lots of 25 and 100, yeah. Okay, so let's do that. I'm going to start writing over here because I've got more room here. So moles iodine in 24, and sorry, in 100 is 4 times that. Which is 6.7 times 10 to the minus 3 moles. Okay, now let's see where that came from. Now, if we look at the original little pictures we've drawn up here, we can see that all of this, the iodine in this, all of that came from just 10 centimeters cubed of bleach. So we can say then that 10 centimeters cubed of bleach contains, all right, oh, we need to go backwards, sorry, before we do that. Sorry, the moles of iodine, so that's equal to the moles of, sorry, I should have said it here. Moles of iodine in 25 centimeters cubed is that. So that means the moles of chlorate we've got are the same, because look, 1 mole of chlorate reacts to give 1 mole of iodine. So the moles of chlorate in 25 is equal to that. So now we have to do the moles of chlorate. So I have to change that in 100. Okay, is equal to that. Right, now this, as we said earlier, this came from 10 centimeters cubed of bleach. So 10 centimeters cubed of bleach contains 6.7 times 10 to the minus 3 moles of chlorate. So that's sodium chlorate. And we want to work out a mass of that. We work out the MR of sodium chlorate. That is equal to 74.5. So now let's do the mass of sodium chlorate. In 10 centimeters cubed of bleach is the moles multiplied by the MR. We do that, that gives us a value of 0.499 grams, sorry, 0.499 grams. Okay, now the question is asking us to, I'm going to go down here, sorry. It asks us to work out the percentage sodium chlorate by mass in the bleach. So we know in 10 centimeters cubed of bleach, we've got 0.499. And earlier it told us that the density of the bleach is equal to 1.20 grams per centimeter cubed. So therefore the mass of 10 centimeters cubed is density times volume. That is equal to, density is 1.2 times 10, that's equal to 12 grams. So the total mass of the bleach of 10 centimeters cubed is 12 grams. And we know that 0.499 of that is sodium chlorate. So the percentage sodium chlorate then is equal to the mass. We've got 0.499 of sodium chlorate divided by the mass of the bleach, which is 12, multiply the whole lot by 100, and we get there a percentage of 4.16. Okay, and that is our final answer. So a 7-mark calculation question with no structure, that's quite intimidating at first. Always these things, it's always best to work backwards, I think. Yeah, to work out your moles of what you can work out, the moles of thiosulfate, even if you're not sure of the way ahead, and that kind of leads you from one step to another. You keep working backwards. And also I do find it helpful to draw little pictures to turn that very wordy question into something that you can visualize more. Okay, right, this is about uncertainty and the burette reading. The uncertainty of the burette is plus or minus 0.155. That's the total uncertainty. What's the total percentage uncertainty? Right, well, our title is 33.5. So the percentage uncertainty is going to be 0.15 over 33.5 times 100. It's going to be pretty small. That's quite a big titer. And that is 0.45%. Not much at all. Okay, now onto an inorganic. This is about group 7. Okay, question about sodium halide. So we're talking about sodium fluoride, sodium chloride, bromide, and iodide, and so on. What is observed when silver nitrate is added to sodium fluoride solution? Nothing happens, no visible change. And the reason for that is because It didn't ask you why, but of course AgF is soluble, unlike all the other silver halides, which are insoluble and will give you a precipitate if you add silver nitrate to solutions of the halide ions. Okay, now 9.2. One observation when solid sodium chloride reacts with concentrated sulfuric acid. Okay, now halide ions have some reducing power, yeah? Br minus, I minus. I minus is not a bad reducing agent because it's quite big. It loses its electrons quite easily. It doesn't ask you this, but I'm just explaining. Chloride ions are not very good reducing agents at all, so you don't get any. So you don't get a redox reaction occurring with the sulfuric acid. The only thing that happens is you'll get an acid-base reaction. Which I'll write it down at the bottom. So you're going to get H2SO4, and that's concentrated plus NaCl. Well, Cl minus, okay. What happens is the Cl minus accepts a proton and becomes HCl gas, okay. And in doing so, you lost a proton from the sulfuric acid. You've only lost one, so you're going to form the HSO4 minus ion. So that's going to be sodium hydrogen sulfate. That would be the equation for it. I'll just show you the ions involved below. Get rid of those now. Okay, now what kind of reaction is that? It's not redox. What would the observation be? Well, you get steamy fumes of HCl. HCl gas is always described as, does look steamy fumes, and it will bubble, okay? What is the role of the chloride ions in this reaction, right? The chloride ions here, well, they're accepting protons, aren't they? So they are acting as a base. They are not acting as a reducing agent, as is the case with bromide and iodide ions. Okay, give an equation for the redox reaction between solid sodium bromide and concentrated sulfuric acid. Okay, right, so let's do that. Now this time you do get a redox reaction. I'm going to construct it from two half equations. Okay, right, bromide ions will get oxidized by the sulfuric acid to bromine. Okay, so you're going to get, you need to put 2 there, and you're going to lose 2 electrons. The sulfuric acid is a mild oxidizing agent, but it can oxidize bromide ions, and in itself it will become reduced to SO2, if you remember, with bromide ions. So let's write the half equation for that. So to make it balanced, we're going to need to have to put in 2H2O there. So that means we need 2H plus there. Balance the electrons, we need 2E minus. So I'm going to write there's 2E minus on both of those half equations. So just combine the two together to get the full equation. So it's going to be 2 bromide ions plus sulfuric acid plus hydrogen ions goes to bromine and SO2 and water. Right, explain using oxidation states why this is a redox reaction. Well, the oxidation number of bromine here is -1, and here it's 0, so the bromine has been oxidized. Whereas the oxidation number of sulfur and sulfuric acid is +6, whereas here it's only +4, so that has been reduced. Okay, it's just knowledge really. There's nothing tricky about that question. Okay, 9.4, what was observed when aqueous chlorine is added to sodium bromide? Well, you do get a displacement reaction there, of course. So give an ionic equation. So right, so we've got Cl2 in aqueous solution, and we're going to need 2 bromide ions. They're in aqueous solution. They're going to each transfer an electron to the chlorines, because the chlorine is an oxidizing agent. So you're going to get 2 chloride ions, and you'll get Br2 in aqueous solution. And that tells us what the observation will be. The solution, we start off with the sodium bromide is a clear solution, a colorless solution. But you'll form bromine in it, so it will turn reddy brown. The chlorine in aqueous solution is just a very, very pale green color. You don't really notice so much. It looks almost colorless. Okay. Right. Now this one here is, we've got an equilibrium reaction here, and we're given the delta H and delta S and entropy data. And we've got to use to work out the Gibbs free energy change. Okay. And of course, the Gibbs free energy change is delta G is equal to delta H minus T, the absolute temperature, delta S. So we need to work out delta H for the reaction here. So they've given us delta H formation for the data values here. So I've made a little Hess's law cycle here. That's the way I like to do it. So I have got the equation top, and down here I've got the elements and the standard states. So in the red arrow going up, all we are doing is we're making 1 mole of carbon dioxide. So that's going to be minus 394 on that arrow. On the green arrow, we're making 1 mole of methanol, which is minus 201, and 1 mole of water in the gaseous phase, so that's minus 242. So if we add those together, we're going to get 443. Now we want to find out delta H, yeah, for that forward reaction there. That's what we need to find out. So delta H, well, you can see there we are going against this red arrow. Going against it, so we change the sign to a plus. And then we're following the green arrow, so we keep the same sign, 443. So delta H there we worked out is equal to minus 49 kilojoules per mole. Now we're going to use that later to put that into our equation there. So we're going to keep that. Now we need to work out the entropy change from these S values. Okay, so we've got to work out delta S now. Right, so delta S, what we need to do is we need to subtract the entropy of the reactants and the products. So let's work out the entropy of the reactants. Well, we've got 1 water, so that's 189. And we've got 1 methanol, so that's 238. And these are in joules, don't forget, not kilojoules per mole per Kelvin. Right, so add that lot up. That comes to 427. Okay. 427 joules. Now let's work out the entropy of the reactant. So we're starting off there. We've got 214, and we've got 3 lots of 131. So add that lot up, and you get that's equal to 607. Okay, so delta S here then is equal to 427 minus 607, so it's a negative entropy change. You can tell it's going to be negative because what you're starting off with 4 moles of gas and you're going down to just 2 moles of gas on that, so the entropy will drop. So it's always good to have a common sense check of the sign. So delta S there is going to be equal to minus 180 joules per mole per Kelvin. But we're going to use that on our delta G equation, so we need to really convert it into kilojoules. So divided by 1,000, it's minus 0.181 kilojoules per mole per Kelvin. Right, now we need to put our numbers into our delta G expression. I'll write it down again. Delta G is equal to delta H minus T delta S. Okay, so delta G is equal to our value of delta H, we worked out was minus 49. Minus, now the T is 890 Kelvin, multiplied by, and what is the value of delta S? Well, that's minus 0.181. Okay, so that gives us minus 49 minus whatever that is. That's 161, okay. Of course, those two minuses become a plus. So our final value is 1 plus 111.2 kilojoules per mole. That's our units of delta G is kilojoules per mole. It doesn't ask us what the significance of that is, but of course it's positive, so it means that reaction is not feasible at that temperature. Okay, but that is just a straightforward putting. A lot of marks there, 6 marks actually, for what is really just kind of quite standard calculation. I think a lot of this paper is not really that, the questions aren't that interesting. They're very straightforward questions. Maybe not like a typical A-level paper. This was the year that not many people did it because of the pandemic. Of course, most people, only the people who didn't like the grades they were given, actually sat this paper, very small number. Okay, and I don't think they made much effort making a good paper, really. Okay, so now figure 4. This shows how the Gibbs free energy change varies with temperature in a different reaction. Okay, so we're talking about different reaction here, and a straight line has been extrapolated to 0. Now, you should know how to, they frequently ask this. So we've got delta G, and we need to know how to linearize this. Delta G is delta H minus T delta S. So we make this fit into the equation of a straight line. Y is equal to mx plus c, and you do this in a few different points in this and the A-level chemistry spec, particularly the Arrhenius equation and stuff. So you should, even if you don't do maths, you should know how to do this. So you're plotting delta G on the y-axis, and on the x-axis we're plotting temperature. Okay, so we've got that x is temperature. So that tells us the gradient of this graph is going to be minus delta S. And the intercept, C, is delta H. Okay, now it asks us to work out delta H and delta S for this reaction. So delta H is really easy. All we're going to do is the intercept on the y-axis, which is of course there. So that's delta H. So we can see there that delta H is equal to minus 149 kilojoules per mole. Now we've got to work out delta S, okay? And it does tell us in the question, we've got to work that out in joules per mole per Kelvin. So we have to be a little bit careful here. But what we need to do is we need to find out the gradient, M, and delta S is the minus gradient. You can see this line has got a negative gradient, so delta S is going to be positive for this reaction, okay? Because M is the negative gradient, okay? So let's work out the gradient. I'm going to use this little triangle here. So there's our change in Y. So delta Y, that's going to be naught minus 149 is minus 149. I'm going to remind ourselves what the units are. That's kilojoules per mole. Now let's do the change in the X in blue there. So delta X is equal to, move that out so I can read it a bit better, then that's 820, isn't it? Yep, 830. Actually, it's not 830, it's 860, isn't it? Look, because that's 900 there, it's 860. So delta X is equal to 860 minus 0 is equal to 860, and the units of that are going to be Kelvin. Right, so what's our gradient equal to? M is equal to the change in Y over the change in X. So that is equal to change in Y. Now that's 149 kilojoules per mole divided by 860 Kelvin. So that gives us 0.17 minus 0.173. And the units of that, well, it's going to be kilojoules per mole over Kelvin. So it's kJ mole per Kelvin. Okay, now that means S, well, S is the negative gradient, so S is equal to plus 0.173 kilojoules per mole per Kelvin. But in the question, it asks us in joules per mole, so we've got to times that by 100. So that's going to be 173 plus 173 joules per mole per Kelvin. All right. Now, what does figure 4 show about the feasibility of this reaction? Well, it shows us, let's have a look at it. Right. So at these low temperatures here, which I'll do in green, look, delta G is positive, okay? So it's not feasible until you get to that point, that temperature there, which is about 860, and then it does become feasible. So what I'm going to write down as my answer. The reaction not feasible below approximately 860 Kelvin. High temperatures higher than that, it should be feasible. Okay, just says state, doesn't explain, so we don't have to really say anything, but that's the answer. Okay, right, on to the very last question, which is about electrochemical cells, and this is not, considering it's quite a big topic, it's not much of a question really, this. It's only 6 marks and fairly straightforward-ish, I suppose. Right, there's no like predicting the direction of a reaction or anything like that, so it hasn't really covered that topic very well. Okay, deduce the half equation for the reaction at the negative electrode. So that tells us the negative electrode, right? Glucose forms carbon dioxide and hydrogen ions. So let's do that. So you've got C6H12O6, and that's going to give us CO2 there. Right. We need to balance with the carbons, first of all. We've got 6 carbons on the left and only 1 on the right, so we need 6 of them. Now we need to balance for oxygens. I've got 12 oxygens on the right and only 6 on this side, so that means I've only 6 H2Os. Now balance for the hydrogens. Well, I have got 12 hydrogens there and another 12 there, so that means I need 24 hydrogens on the right-hand side. 24 H plus ions. Now balance for the charges. I've got no charge on the left, 24 plus on the right, so I need 24 electrons. Okay, deduce the half equation for the positive electrode. Okay, now the positive electrode, it says oxygen gas here reacts with H plus ions to form water. Okay, so here we've got O2 and it's going to form H2O here. We need to balance the number of oxygens, so we need a big 2 there. So that means we're going to need 4 H pluses on this side. Balance of the charges, no charge on the right, 4 plus on the left, so I need 4 electrons here on the left. Okay, so given an overall equation for the reaction that occurs in the glucose oxygen fuel cell, well, you can see here we've got 24 protons here, and we have got only 4 here, so I'm going to have to multiply that by 6. And that's going to give us 24 H pluses then, 4 times 6, yeah, 24, we've got 24 there, so they're all going to cancel out. So we're going to simply end up, and the electrons are obviously going to cancel out. The overall equation is going to be, you've got glucose, C6H12O6. We have to times this one by 6. We've got 6 oxygens there. All the protons are all going to go. So just basically the equation for respiration, 6 CO2 and 6 H2O. Obviously that's okay. Yeah, we're going to get some of these H2Os cancelling out on both sides of the equation. So that is the right number. You check that. So okay, that's the correct equation. Right. The negative electrode is made of carbon, the positive electrode is made of platinum. Now we need to construct the conventional representation. So I'm going to draw my salt bridge here in the middle. The convention is to put the positive electrode on the right, which is the oxygen one. And I need to put So the oxidized species here is oxygen and the reduced species is water. So I need to put O2 next to the salt bridge. Now that's a gas, and we need to put the hydrogen ions in as well. So we've got a phase change there, hydrogen ions. And then we've got the reduced thing, which is water. There's no phase change, that's H2O. It says we've got platinum there, so we need to put another phase change and PT for the metal there. Let's do it for the other one then. Okay, for the negative electrode, which should go on the left. So we are going to have, we've got glucose. We've got glucose there. And we've got carbon dioxide and H plus as the oxidized form. The oxidized form next goes to the next salt bridge. So I need to have CO2 here. It's a phase change, and we're going to have H plus as well. And then we're going to have in solution, we're going to have glucose, the reduced form, C6H12O6. And we're going to have a phase change for the electrode then, which is carbon. So that's our overall equation there. Okay, what must be done to maintain the EMF of this fuel cell when in use? Well, we've got to keep providing glucose, fuel, and oxygen. As they get used up, so you've got to keep the concentrations of them the same so the EMF doesn't change. It's a fuel cell, so we provide the products, the reactant, sorry. Okay, and that is the last question on the paper. That's the end.